This shaft descends 530 meters straight into the earth. A cable runs down its center. At the bottom, a weight. When that weight rises, it stores energy. When it drops, it generates electricity. No battery, no chemistry, no degradation. The physics is 150 years old and one company is building it. 550,000 mine shafts are sitting idle across the United States right now. Each one descends hundreds of meters straight into the earth. Each one already has a grid connection. Right now, they are doing nothing. Meanwhile, lithium-ion battery facilities are being built on flat land at a cost of $300 to $400 per kilowatt hour of storage capacity, using materials mined in the Democratic Republic of Congo, processed in China, and shipped across 2 oceans before they reach a construction site in Texas or Nevada. Those mine shafts can store grid electricity at a cost of $1 to $10 per kilowatt hour. No lithium, no cobalt, no chemistry. Nothing but gravity, a cable, and a weight. But if that physics is that straightforward, and if abandoned mines are that abundant, 550,000 of them in the United States alone, according to a published IIASA study, why is only one company seriously building these systems? And should you care? The principle behind mineshaft gravity storage is not new. It is not even recent. The first utility-scale application of gravity as stored energy came in the 1880s, when Swiss and Italian engineers began building pumped hydro facilities, using surplus electricity from early power plants to push water uphill, then releasing it through turbines when demand peaked. The Armstrong hydraulic accumulator, installed in industrial docks across northern England in the 1870s, used the weight of a loaded piston in a vertical cylinder to store hydraulic pressure for cranes and lifts. Gravity as a storage medium is 150 years old, but all of those systems required either a specific geography, mountains and water, or purpose-built infrastructure that cost as much as the energy it stored. Gravitricity, a company founded in Edinburgh, Scotland by inventor Peter Franco, who previously designed the world's first full-scale tidal energy turbine, recognized in the 2010s that something had changed. The world now had hundreds of thousands of abandoned vertical shafts, already excavated to depth, already connected to the grid, sitting idle as liabilities. The infrastructure problem was already solved. The mining industry had solved it over a century of digging. The mechanism operates on 3 compounding physics principles. Gravitational potential energy increases with mass and height. The heavier the weight and the deeper the shaft, the more energy it can store. An electric motor acting as a generator converts the kinetic energy of the descending weight into electricity through Faraday's electromagnetic induction. And regenerative braking, the same principle used in every electric vehicle, controls the rate of descent precisely on determining whether the system releases energy in a sub-second burst or a slow 8-hour trickle. But here is what most reviews of this technology miss. It is the decoupling of power capacity from energy capacity that makes the mine shaft format uniquely useful to grid operators. In a lithium-ion battery, the amount of power you can discharge at once is locked to the amount of energy stored. In a Gravistore system, power output is determined by the speed of the winch motor. Energy stored is determined by the weight and the depth. They are independent variables. Grid operators can tune each one separately. That is a design flexibility no battery chemistry currently matches. Gravitricity built and publicly demonstrated a 250 kilowatt prototype in Edinburgh in 2021. It went from 0 to full power in less than 1 second. A response time faster than most grid stabilization batteries and roughly 20 times faster than pumped hydro. The demonstrator was validated by an independent assessment from Imperial College London in 2018, which identified the technology as a compelling alternative to conventional storage, citing the extended lifespan and power-to-energy cost ratio as the primary advantages. The company has since signed a partnership with ABB, the Swedish-Swiss industrial giant that manufactures the majority of the world's mine hoisting equipment, to accelerate deployment. ABB's involvement is not incidental. It is a signal, A BB does not partner with technology that has not passed internal engineering review. The company also brought in Huisman, a Dutch specialist in deep water and heavy lift winch systems. Both partners supply the core mechanical infrastructure that makes the system work at scale. In February 2024, Gravitricity announced the first full-scale commercial deployment at the Pyhäsalmi mine in Pyhäjärvi, Finland, Europe's deepest zinc and copper mine, descending 1,444 meters into the earth. The project uses a 530-meter deep auxiliary shaft and will deliver up to 2 megawatts of storage capacity directly into the Finnish national grid. But the real question is not whether the technology works at the Pyhäsalmi mine. The question is whether it works for you, and that answer is more complicated than the physics suggests. The performance data for the Gravistore system is specific and independently sourced, round-trip efficiency of 80 to 90%. Sub-second response from 0 to full rated power, a design lifespan of 50 years with no cycle limit and no performance degradation. A published Science Direct paper from the University of Oxford 2019 confirmed the round-trip efficiency assumption of 80% as structurally sound based on motor and power electronic specifications. Compare that directly to lithium-ion grid storage. Lithium-ion achieves 90 to 95% round-trip efficiency, higher than gravity, on that specific metric. But lithium-ion degrades. The storage capacity of a lithium-ion system drops measurably over 500 to 6,000 charge cycles, depending on chemistry, depth of discharge, and thermal management. A gravity storage system has no chemistry to degrade. The weight does not wear out. The shaft does not corrode. The only degradation pathway is mechanical, in the winch and motor, components with documented service intervals and replaceable parts. On cost, the comparison is stark. A 2023 IIASA study published in the journal Energies from the International Institute for Applied Systems Analysis in Austria calculated underground gravity energy storage investment costs at $1 to $10 per kilowatt hour. Lithium-ion grid storage costs in the same period ran $300 to $400 per kilowatt hour of installed capacity. That is a 30 to 300-fold cost advantage depending on site conditions. The IIASA study estimated the global storage potential of underground gravity energy storage in abandoned mines at 7 to 70 terawatt hours. To calibrate that figure, 70 terawatt hours is roughly equivalent to global daily electricity consumption. The United States alone has over 550,000 abandoned mines, with China, India, Russia, and the US identified as the highest potential geographies. Each Gravistore installation can store more than 20 megawatt hours per shaft and output between 1 and 20 megawatts of power. A 10,000-ton mass raised 100-meter stores approximately 2.7 megawatt-hours of potential energy, enough to power roughly 250 average American homes for 1 hour per cycle, repeatedly, for 50 years, with no chemical degradation of any kind. And this is where the honest answer starts to depend on who is asking. But these numbers come with an important caveat. And it is a significant part of the reason why only one company is seriously building these systems right now. The first limitation is energy density. A published Science Direct review of solid gravity energy storage systems documents it directly. Gravity storage systems achieve approximately 0.1 to 0.5 watt-hours per kilogram of system mass. Lithium-ion achieves 150 to 400 watt-hours per kilogram. That is a 300 to 800-fold difference. A mine shaft gravity system needs thousands of tons of mass and hundreds of meters of vertical drop to store what a lithium-ion facility achieves in a warehouse. The physics of gravitational potential energy is simply less dense than electrochemistry. The second limitation is shaft geometry. A 2019 paper published in Applied Energy by researchers at the University of Oxford documents it specifically. The energy storage capacity of mine shafts with small diameters is limited because increasing the mass requires a relatively larger increase in the height of the cylindrical weight, reducing the usable shaft depth. Narrow shafts produce constrained economics. Not every abandoned mine is suitable. The third limitation is geography. Mine shaft gravity storage requires an existing deep mine shaft at a location that is also connected to the grid and proximate to renewable generation that produces surplus power worth storing. That three-condition intersection, deep shaft, grid connection, renewable surplus, is not universally distributed. A large fraction of the 550,000 abandoned U.S. mines do not satisfy all three conditions simultaneously. Identifying which ones do requires site-by-site feasibility analysis. The market explanation for why only one company is seriously building these systems is structural, not conspiratorial. Lithium-ion battery costs fell by 97% between 1991 and 2023, the fastest cost decline ever documented for an energy technology. No gravity storage startup could raise capital against that price curve during the period when lithium-ion was falling fastest. The investment thesis for gravity storage only becomes compelling when lithium-ion costs stop falling and the need for long-duration, low-degradation storage at specific grid locations makes the site-specific economics work. That moment is now arriving. It has not yet arrived at scale. So the real question is whether you should care about underground gravity energy storage. And the honest answer depends entirely on where you sit in the energy system. If you are a grid operator managing renewable intermittency in a region with abandoned deep mines, this technology is directly relevant to your procurement decisions today. The Pyhäsalmi deployment is the proof of concept that makes the next conversation possible. If you are a homeowner or small commercial operator looking for behind-the-meter storage, it is not. The physics and economics of mine shaft gravity storage are fundamentally utility scale. A residential gravity storage system would require lifting multi-ton masses to significant heights. A lithium-ion battery is simply the better solution at that scale, and there is no honest case to make otherwise. The competitor product that wins for the residential and small commercial viewer is a lithium iron phosphate battery system, specifically LFP chemistry, which achieves 3,000 to 6,000 cycles before significant degradation compared to the shorter cycle life of standard lithium-ion and carries no cobalt in the supply chain. It does not have a 50-year lifespan, but it exists, it is certifiable, and it works where gravity storage cannot. Peter Franco designed Gravitricity after spending years watching the tidal energy sector fail to scale, not because the physics was wrong, but because the infrastructure costs of purpose-built ocean installations made the economics unworkable at every project stage. His insight with mineshaft gravity storage was the same insight Robert Stirling had with the heat engine. Do not build the infrastructure. Use infrastructure that already exists and was already paid for by someone else's industry. The Pyhäsalmi mine was dug between 1962 and 2022. Over 60 million tons of ore were extracted. More than 200 million euros in community tax were paid over its operating life. The shaft is there, the grid connection is there. The weight can be sourced locally. The only thing missing from a 50-year, low-cost, zero-degradation grid storage system was someone willing to treat a decommissioned mine as an asset rather than a liability. Gravitricity is currently the only company building these systems at full scale. That will change when the Pyhäsalmi prototype demonstrates performance in a live grid environment. The question is not whether it works. The question is how fast the world gets serious about the 550,000 shafts it has already dug. If you want to understand how the same gravitational physics principle applies at residential scale, what works, what does not, and what the actual cost comparison looks like, that analysis is in the next video.